Welcome to this lecture on algorithms. Now, algorithms are meant to solve problems. So in this first segment, we're going to start discussing the difference between problems and problem instances. Now, many problems are related to each other. And in fact, many problems are instances of more general problems. So for example, one problem I face quite a bit is to look up a student's name in a class roster. Let's say I'm looking for Ben in some class roster. Well, more likely I will be looking for some other student's name in either the same class roster or in a different one. That happens all the time. So it's beneficial to realize that these two problems are related. In fact, there are two special cases or two instances of the same problem. So that's the difference between an instance of a problem and a general problem. So let's continue this example by specifying what the general problem could be. See, the general problem is more abstract or more general than the instances. It could be stated as finding someone's name in some class roster. Notice I started with Ben and Abby, and then I abstracted away and realized, well, those are both someone's name. And similarly, I can generalize over the class roster, and I can define the problem taking, in essence, two variables that are underlined in blue here, which is someone's name and some identifier for a class. And given those two, I can search for that name in that particular class roster. Once I give a specific value for the variables in the problem, I get what's called a problem instance. So if I assign the name Abby to someone's name, and I assign CS221 to some class, then I get a particular instance of that problem. Now, there are advantages to recognizing that two problems are similar, or that two problems are actually instances of a more general problem. So the first advantage I want to mention is that once you have found a solution to a problem, if the problem covers many instances, then you only have to write one solution to solve all of the instances. That's a pretty major time-saving solution. A second advantage is that the general problem is more general by definition. It's more abstract. And therefore, it can more easily be modeled mathematically, which means we can use some common known discrete structures to solve it. And that's a big advantage because that way we don't have to define our own structures. We can reuse some well-known structures that are useful in many different problems. So going back to our example, turns out we can generalize our problem here and we can make it even more abstract. We can realize that we can now forget about the details of only looking into rosters. And maybe we can forget about looking for someone's name. What if we were looking for anything and we were looking for it inside some kind of collection of objects? In particular, let's consider the following problem, which is an abstraction of this problem. It says, find an item in a sequence of items. First of all, an item is more general than someone's name. It doesn't have to be a name. It could be almost anything. And a sequence of items is a generalization of a roster. And remember that by sequence, in mathematics, we mean an ordered sequence. So it's not a set. It's one of those special kind of functions where the domain is the set of integers. So let's say we generalize our problem to this one. And let's say we found a solution to this problem. Then we would be able to solve a very large number of problem instances like the one we talked about before. What if the item is someone's name? And what if the particular sequence of items is a class roster for a particular class? So we could solve our earlier problem instances with this solution, but we could also solve unrelated problems like finding someone's email address in a contact list, or finding a particular book on a bookshelf. So in conclusion, the advantages of identifying the general or abstract features of a problem are that by abstracting away the details, we can focus on the important discrete structures that the problem can be modeled with, and also we can write a single solution that will be useful for a large number of problem instances. Now that we're clear about the difference between problems and problem instances, let's turn our attention to the main topic of this lecture, which is algorithms. So let's define an algorithm. An algorithm is the specification of a sequence of instructions in order to solve a problem, a general problem. Now, to be an algorithm, you must have the following properties. These are required properties of an algorithm. First of all, the set of acceptable inputs to the algorithm, that is, the set of all the problem instances that it's supposed to handle, must be fully specified. There can't be any ambiguity in terms of what are the acceptable inputs to the algorithm. Second required property is that the correct answer to each and every problem instance must be fully specified. In other words, you must fully specify the input and the output of the algorithm. Not only that, but the algorithm must always produce the correct answer for each and every problem instance. Otherwise, it's not a correct algorithm. It's not an answer to the problem. The third requirement is that each instruction in the algorithm be completely well defined or definite. There cannot be any ambiguity as to what the instruction means. And also, each instruction must be executable in a finite amount of time. So let me give you two counterexamples of directions, say, that are not instructions. What if one instruction in the algorithm said, paint the house blue? Well, that's not definite enough. First of all, you didn't specify which specific shade of blue. You didn't specify which parts of the house. Do you paint the roof as well? Do you paint the inside, the outside? And so on and so forth. There are much ambiguity in that instruction. So it's not definite, it's not a valid instruction. Second, consider the instruction, print all the prime numbers. Well, that's pretty specific and not very ambiguous. The problem is it's impossible to execute this instruction in a finite amount of time given that there are an infinite number of prime numbers. So these are the meanings of the third required property of algorithms. The fourth required property is that the number of instructions that make up the algorithm must be finite. So by definition, an algorithm is finite. You can't use, say, ... like we do in an infinite set to define the instructions in an algorithm. It must have, by definition, a finite number of instructions. And the last and fifth required property of an algorithm is that not only the number of instructions is finite, the source code, if you wish, of the algorithm is finite, but when you execute the algorithm, it must also terminate in a finite number of steps. You're probably aware that an algorithm can contain a loop, and even if the loop has a finite number of instructions in it, it could still run for an infinite time if you have what's called an infinite loop. Well, that is not acceptable in an algorithm. An algorithm must always produce an answer, and of course, it must always produce the correct answer, as we specified here. And it must do so in a finite amount of time. It must always terminate with a correct answer. So, to conclude this first segment, I want you to think about the problem we talked on the previous slide of finding an item in a sequence of items, and to come up with an algorithm and to write it down very specifically and clearly and unambiguously. So find an algorithm that solves the previous problem and that has all 5 of these properties.